how even the faintest rings are influenced by gravitational interactions and the ongoing exchange of material within Saturn's system. Perhaps the most Have you ever looked at images of Saturn and wondered about the magnificent rings surrounding this gas giant? How did they form? What mysteries do they hold? These shimmering bands are more than just a cosmic decoration. They're windows into the early days of our solar system. Are you ready to uncover the secrets of Saturn's rings and explore their fascinating role in shaping the cosmos? Join us as we dive into one of the most captivating mysteries of the universe. A cosmic masterpiece, Saturn's stunning rings. Saturn's rings are one of the most breathtaking sights in our solar system, capturing the imagination of astronomers and dreamers alike. These shimmering bands of ice and rock span an incredible width of over 175,000 miles, yet they're surprisingly thin, often no thicker than a few stories of a building. This delicate structure gives them their ethereal beauty and makes them a wonder of cosmic engineering. Each ring is made up of countless particles, ranging in size from tiny grains of dust to massive chunks as large as a small house. These particles are primarily composed of water ice, which reflects sunlight and gives the rings their dazzling appearance. Despite their apparent simplicity, the rings' intricate composition and structure continue to baffle and amaze scientists. The rings are divided into distinct segments labeled alphabetically, including the A, B, and C rings. Each segment has unique characteristics, such as variations in particle density and composition. For example, the Cassini division, a dark gap between the A and B rings, is caused by gravitational interactions with Saturn's moon Mimas, showcasing the complex dance of celestial mechanics. What's even more astonishing is the constant activity within the rings. Collisions, gravitational interactions, and the influence of Saturn's many moons create a dynamic environment where particles are continuously moving, clumping together, and breaking apart. This activity has helped scientists study the principles of planetary formation on a smaller scale, providing insights into how the solar system evolved billions of years ago. Saturn's rings aren't just a visual spectacle, they're a scientific treasure trove. Their unique characteristics and dynamic nature make them an unparalleled laboratory for studying the mysteries of planetary systems and the forces that shape them. The birth of the rings, ancient or recent origins. The origin of Saturn's rings has been a topic of intense debate for decades. Some scientists believe they formed alongside Saturn over 4 billion years ago, while others argue that they're a relatively recent addition to the planet's history. Both theories offer fascinating insights into the workings of our solar system. The ancient origin theory suggests that the rings are remnants of the primordial material that formed Saturn. In this scenario, the rings are made of icy particles that failed to coalesce into a moon, remaining in orbit around the planet instead. This theory aligns with the idea that the rings are as old as Saturn itself, providing a window into the solar system's early days. On the other hand, recent evidence from NASA's Cassini spacecraft points to a younger origin, possibly just a few 100 million years ago. This theory proposes that the rings were formed when a comet or a moon was torn apart by Saturn's gravity, scattering icy debris into orbit. The relatively pristine nature of the rings supports this idea, as they show little evidence of long-term contamination by interplanetary dust. Interestingly, both theories may be partially correct. It's possible that Saturn had older, primordial rings that were later rejuvenated by the addition of fresh material from a disintegrated moon or comet. This would explain the rings' youthful appearance while preserving their connection to Saturn's ancient past. Understanding the rings' origins isn't just about solving a cosmic mystery, it's also about unraveling the history of our solar system. By studying the forces that shaped Saturn's rings, scientists can gain a deeper understanding of the processes that created planets, moons, and other celestial bodies billions of years ago. Cassini's legacy, unlocking the rings' mysteries. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, revolutionized our understanding of the planet and its rings. Equipped with state-of-the-art instruments, Cassini conducted detailed observations that revealed the rings' stunning complexity and dynamic behavior. One of Cassini's most groundbreaking discoveries was the sheer diversity within the rings. High-resolution images showed intricate patterns, including wave-like structures caused by the gravitational pull of Saturn's moons. These waves act as a cosmic fingerprint, providing clues about the moon's orbits and the ring's composition. Cassini also uncovered fascinating details about the ring's mass and age. By studying how the rings scattered radio waves, the spacecraft measured their density and determined that they were surprisingly lightweight. This finding supports the idea that the rings are relatively young, as older rings would have accumulated more debris over time. Another remarkable discovery was the interaction between the rings and Saturn's upper atmosphere. Cassini detected a steady flow of material from the rings into the planet's atmosphere, a process dubbed ring rain. This phenomenon suggests that the rings are slowly disintegrating, and they may disappear entirely in a few 100 million years, a fleeting moment in cosmic terms. Cassini's final mission, the grand finale, involved a daring dive between Saturn and its rings. This maneuver provided unprecedented data on the ring's composition and structure, leaving behind a treasure trove of information for scientists to analyze. The spacecraft's legacy continues to inspire awe and curiosity, highlighting the value of exploration in unlocking the secrets of the cosmos. Shepherd moons, guardians of the rings. Saturn's rings owe much of their stability to a unique group of celestial companions known as shepherd moons. These small moons orbit near or within the rings, using their gravitational influence to shape and maintain the delicate structure of the bands. Each shepherd moon plays a specific role in the ring's dynamics. For instance, the moonpan carves out the Encke gap in the A ring, while Prometheus and Pandora work together to sculpt the edges of the F ring. These moons act as cosmic gardeners, clearing debris and creating striking features within the rings. The interactions between shepherd moons and ring particles are a perfect example of the delicate balance of forces in the universe. As a moon passes near the rings, its gravity pulls on the particles, creating ripples and waves that propagate outward. These interactions prevent the particles from spreading too far apart, ensuring the rings remain well-defined. Shepherd moons also highlight the interconnectedness of Saturn's system. Their influence extends beyond the rings, affecting the orbits of other moons and contributing to the planet's overall gravitational dynamics. This interconnected web of interactions offers a glimpse into the complexity of planetary systems and the forces that govern them. By studying shepherd moons, scientists can gain valuable insights into similar processes in other parts of the universe. These tiny moons serve as natural laboratories, helping us understand how gravitational forces shape celestial structures on both small and large scales. A closer look at composition. What are Saturn's rings made of? Saturn's rings are a celestial wonder composed of billions of particles, yet their makeup is surprisingly straightforward. Most of the material is water ice, giving the rings their brilliant, reflective appearance. These icy particles are mixed with smaller amounts of rocky debris and dust, hinting at a dynamic history of collisions and interactions within Saturn's system. The water ice that dominates the rings reflects sunlight so effectively that it creates the illusion of a solid structure. However, up-close observations from the Cassini spacecraft revealed the true nature of these rings as vast collections of individual particles. These particles range in size from tiny grains of sand to boulders several meters across, creating a complex and ever-changing environment. Spectroscopic analysis has uncovered subtle differences in the composition of each ring segment. For example, the B ring is particularly dense and bright, suggesting a higher concentration of larger ice particles. In contrast, the C ring contains more dust, which gives it a darker appearance. These variations point to a history of different origins and influences for each ring, shaped by Saturn's gravitational forces and its moons. Interestingly, the material in the rings appears to be relatively pure. This purity suggests that the rings have not been significantly contaminated by interplanetary dust over time, lending support to the theory that they are younger than Saturn itself. The bright, pristine ice also raises intriguing questions about their origin. Were they formed from a disintegrated moon, a shattered comet, or even leftover material from Saturn's formation? The composition of Saturn's rings provides a snapshot of the dynamic processes that shape planetary systems. By studying the distribution and properties of their material, scientists can gain valuable insights into the formation and evolution of not only Saturn's rings, but also other cosmic structures throughout the universe. The mysterious heat phenomenon, rings that glow in the dark. Saturn's rings have long been admired for their shimmering beauty, but recent discoveries reveal a hidden, glowing side to them. This phenomenon, first detected during solar occultations observed by the Cassini spacecraft, shows that the rings emit their own heat. This unexpected discovery has sparked new questions about the forces at play within this cosmic masterpiece. The heat emission is particularly pronounced in the dense B ring. Scientists believe this is due to the way particles within the ring interact and generate friction. As the particles collide and rub against each other, they release thermal energy, causing the ring to radiate heat. This process is more intense in regions with a higher density of particles, creating distinct patterns that align with the ring's structure. Another contributing factor to the heat phenomenon is the effect of sunlight. During the day, the ice particles in the rings absorb solar radiation, which they slowly release as heat during the night. This interplay between solar heating and thermal radiation creates a fascinating cycle that reveals the dynamic behavior of the ring particles. What makes this discovery even more intriguing is the possibility that the heat emissions could provide clues about the ring's age and evolution. The patterns of thermal radiation suggest ongoing activity within the rings, indicating that they are not static but rather in a state of constant flux. This dynamic nature could explain why the rings have remained so well defined, despite the forces working to spread their material. The heat phenomenon adds a new layer of complexity to our understanding of Saturn's rings. It's a reminder that even the most familiar celestial objects still hold surprises, challenging us to look deeper and uncover the hidden processes that shape our universe. The faint rings, discovering Saturn's hidden features. While Saturn's main rings often steal the spotlight, the planet is also surrounded by a collection of faint, less visible rings that extend far beyond the familiar A, B, and C rings. These faint rings, including the E and G rings, were discovered using advanced imaging techniques and have revealed a more intricate and expansive ring system than scientists had previously imagined. The E ring is one of the most fascinating of these faint rings. Unlike the dense inner rings, the E ring is composed of microscopic ice particles that are continually replenished by the icy moon Enceladus. Geysers on Enceladus's surface eject water vapor and ice into space, much of which becomes trapped in orbit around Saturn, forming the diffuse E ring. This dynamic relationship showcases the interconnectedness of Saturn's rings and moons. The G ring, another faint ring, is thought to be shaped by the moon Aegeon, which orbits within the ring. Aegeon's surface material is likely eroded by micrometeorite impacts, contributing to the sparse population of particles in the G ring. This highlights how even the faintest rings are influenced by gravitational interactions and the ongoing exchange of material within Saturn's system. Perhaps the most intriguing of all is the discovery of the Phoebe ring, an enormous and extremely faint structure that orbits far beyond Saturn's main ring system. Composed of dark, dusty material, this ring is likely formed from debris ejected by impacts on the irregular moon Phoebe. Despite being invisible to the naked eye, the Phoebe ring is one of the largest structures in the solar system, stretching millions of miles across. These faint rings remind us that Saturn's beauty extends far beyond what we can see. By studying these subtle features, scientists can explore new dimensions of planetary ring systems and uncover connections between moons, rings, and the processes that shape them. Saturn's rings and the solar system's past. Saturn's rings are more than just a stunning feature of the planet. They are a time capsule of the solar system's history. By examining their composition, structure, and behavior, scientists can gain valuable insights into the early days of the solar system and the processes that shaped its evolution. The ring's icy composition suggested a connection to the early solar system, when icy bodies were abundant and collisions were more frequent. These collisions may have played a key role in the formation of the rings, shattering moons or comets and scattering their material into orbit around Saturn. The remnants of these ancient events are preserved in the rings, providing a glimpse into a time when the solar system was still taking shape. Gravitational interactions within the rings mirror the forces that govern the motions of planets and moons. By studying the behavior of ring particles and their interactions with Saturn's moons, scientists can model similar processes that occurred during the formation of planetary systems. The rings serve as a miniature version of the early solar system, allowing researchers to test theories and refine our understanding of planetary formation. Saturn's rings also shed light on the life cycle of planetary systems. The ongoing ring rain phenomenon, where material from the rings falls into Saturn's atmosphere, illustrates how planetary systems evolve over time. This process highlights the transient nature of ring systems, suggesting that Saturn's rings may be a temporary feature in the planet's long history. Understanding Saturn's rings helps us appreciate the interconnectedness of the solar system. They are not isolated structures, but rather integral components of a dynamic, evolving system that continues to shape our understanding of the cosmos. By studying Saturn's rings, we not only unlock the secrets of a single planet, but also uncover clues about the origins and destiny of the solar system itself. That wraps up our journey through the secrets of Saturn's rings, a stunning masterpiece of the cosmos. From their mysterious origins to their dynamic interactions with Saturn's moons, these rings remind us of the incredible beauty and complexity of our solar system. If you enjoyed this deep dive, be sure to like, share, and subscribe to InnoVision Tech. Don't forget to hit the bell icon to stay updated with our latest explorations. Until next time, keep reaching for the stars. Have you ever wondered what lies beyond the planets of our solar system? Beyond Neptune, a fascinating world of mysterious and lesser-known celestial bodies called dwarf planets awaits exploration. How are these worlds different from planets, and why do they captivate astronomers worldwide? Join us as we embark on an incredible journey to uncover the secrets of the dwarf planets in our solar system and explore their unique features and discoveries. Pluto, the trailblazer of dwarf planets. Pluto was the 9th planet of the solar system until 2006, when its reclassification sparked global debates. This icy world, located in the Kuiper Belt, is a fascinating dwarf planet that orbits the Sun over 248 Earth years. Despite being demoted, Pluto remains a captivating celestial body that continues to reveal secrets about our solar system. At 2,377 kilometers in diameter, Pluto is roughly 2/3 the size of Earth's moon. Its surface is a frozen expanse of nitrogen, methane, and carbon monoxide ice, with vast plains like Sputnik Planitia and towering ice mountains. Pluto also boasts a surprisingly dynamic atmosphere that expands and contracts with its elliptical orbit, showcasing how even the coldest worlds can exhibit complex weather patterns. Pluto's moon system adds another layer of intrigue. It has 5 known moons, with Charon being the largest and most remarkable. Charon's size, half that of Pluto, creates a unique relationship between the two, as they orbit a shared gravitational point. This binary system offers insights into how celestial bodies can evolve together in isolated regions of space. NASA's New Horizons mission, which flew by Pluto in 2015, revolutionized our understanding of this dwarf planet. The spacecraft sent back stunning images and data, revealing unexpected geological activity and potential subsurface oceans. These findings hinted that Pluto may harbor conditions suitable for some form of life, redefining what is possible in extreme environments. Pluto's story is far from over. As one of the most well-studied dwarf planets, it serves as a window into the mysteries of the outer solar system, demonstrating that even small celestial bodies can have monumental significance. Ceres, the smallest giant in the asteroid belt. Ceres stands out as the only dwarf planet located in the asteroid belt between Mars and Jupiter. Discovered in 1801, Ceres was once considered a planet before being classified as an asteroid, and finally as a dwarf planet in 2006. This unique classification underscores its importance in bridging our understanding of planetary and asteroid characteristics. With a diameter of about 940 kilometers, Ceres is the smallest recognized dwarf planet but holds massive scientific interest. Its surface is a mix of rock and ice, punctuated by bright spots like those in the Ocketer crater. These spots are deposits of sodium carbonate, a salt left behind by water activity. Such discoveries suggest that Ceres may once have had a subsurface ocean, and remnants of liquid water could still exist today. The Dawn spacecraft, which orbited Ceres from 2015 to 2018, revealed surprising geological features, including cryovolcanoes. Ahuna Mons, for example, is a towering ice volcano that indicates Ceres may still be geologically active. The presence of organic compounds on its surface also raises intriguing questions about the potential for prebiotic chemistry. Ceres' location in the asteroid belt makes it a unique laboratory for studying the building blocks of planets. Scientists believe it formed early in the solar system's history, preserving ancient materials that can provide clues about the conditions during its formation. As missions to Ceres continue to be proposed, this small world holds immense promise for unraveling the mysteries of planetary formation and the potential for life beyond Earth. Ceres is a reminder that size is no limitation when it comes to cosmic significance. Haumea, the peculiar oval world. Haumea is one of the most unusual dwarf planets, recognized not only for its elongated shape but also for its rapid rotation. This celestial oddity resides in the Kuiper Belt and is named after the Hawaiian goddess of fertility and childbirth. Its unique characteristics make it a captivating target for astronomers and planetary scientists. Unlike other dwarf planets, Haumea has a distinctly oblong shape, which is a direct result of its incredibly fast rotation. Completing a spin in just 4 hours, this rapid rotation has stretched Haumea into an oval, a phenomenon rarely seen on such a large scale. This unique shape provides insights into the effects of angular momentum on celestial bodies. Haumea is also notable for its composition. Its surface is largely covered in crystalline water ice, making it one of the brightest objects in the Kuiper Belt. This icy exterior hints at past collisions or geological activity that brought fresh ice to the surface. These impacts may also explain Haumea's 2 small moons, Hi'iaka and Namaka, which orbit it today. Another fascinating feature of Haumea is its ring system. Discovered in 2017, the ring adds to its distinctiveness as one of the few known dwarf planets with this characteristic. The ring likely formed from debris left behind by ancient collisions, showcasing the dynamic processes that shape the Kuiper Belt. Haumea's peculiarities continue to challenge and expand our understanding of dwarf planets. Its rapid rotation, unique shape, and icy composition offer a glimpse into the diverse ways that celestial bodies evolve in the distant reaches of the solar system. A Makemake, a frozen world with a fiery name. Makemake, named after the Rapa Nui deity of creation, is another Kuiper Belt resident that adds to the diversity of dwarf planets. Its icy surface and distant orbit make it one of the coldest known objects in our solar system, offering an extreme environment for scientific exploration. Measuring about 2/3 the size of Pluto, Makemake is the second brightest object in the Kuiper Belt. Its surface reflects a significant amount of sunlight due to a layer of frozen methane, ethane, and possibly nitrogen. These icy compounds contribute to its reddish hue, a feature that distinguishes Makemake from other celestial bodies. Despite its frozen nature, Makemake has shown signs of an atmosphere, albeit a temporary one. Observations suggest that its thin atmosphere forms when it is closest to the sun and freezes when it moves away. This cyclical atmospheric behavior provides clues about the volatile substances present on its surface. Makemake's moon, discovered in 2016, adds to its intrigue. This tiny satellite, informally named MK2, is a dark, rocky body that contrasts with the brightness of Makemake itself. The moon's presence offers scientists an opportunity to measure Makemake's mass and density more accurately, improving our understanding of its internal composition. Makemake's study is still in its early stages, but its unique characteristics make it a compelling target for future missions. As we continue to explore, this icy dwarf planet will likely reveal more about the dynamics and diversity of the outer solar system. Eris, the most distant dwarf planet. Eris, one of the most intriguing dwarf planets, resides in the scattered disk region of our solar system, far beyond Pluto. Its discovery in 2005 played a pivotal role in the reclassification of planets, including the demotion of Pluto to a dwarf planet. Named after the Greek goddess of strife, Eris lives up to its name by challenging our understanding of the outer solar system. Eris is slightly smaller than Pluto, but is the most massive dwarf planet discovered so far. Its high density suggests a composition rich in rock and ice, differentiating it from the gas giants that dominate the outer regions of the solar system. This composition aligns with theories about how icy bodies formed in the cold reaches beyond Neptune. One of the most fascinating features of Eris is its reflective surface. which rivals that of freshly fallen snow. This brightness is due to a thin layer of methane ice, indicating that it may have undergone surface renewal processes in the past. These observations suggest a dynamic history that includes the possibility of cryovolcanism or other geological activity. Eris is accompanied by a small moon named Dysnomia. This moon provides crucial data for calculating Eris's mass and understanding its gravitational interactions. Observations of Dysnomia's orbit allow scientists to estimate the density of Eris, giving insights into its internal structure and formation history. Eris's extreme distance from the Sun places it in one of the most isolated regions of our solar system. This distance poses significant challenges for exploration, but Eris remains a priority for future missions seeking to unlock the secrets of the scattered disk. Its discovery and study continue to reshape our view of the outer reaches of the solar system, demonstrating that there is still much to learn about the worlds beyond Neptune. Sedna, a mystery on the solar system's edge. Sedna, named after the Inuit goddess of the sea, is one of the most enigmatic objects in the solar system. Discovered in 2003, this distant dwarf planet resides in the far reaches of the solar system, in a region known as the Inner Oort cloud. Its extreme orbit and unique characteristics make it a key piece in understanding the early formation of our solar system. Sedna's highly elliptical orbit takes it on a journey that spans thousands of years. At its closest approach, Sedna is still over 76 astronomical units away from the Sun, nearly 3 times farther than Neptune. At its farthest, Sedna ventures nearly 1,000 AU away, a distance that places it among the most isolated objects in the solar system. With a reddish surface, Sedna's color suggests a composition rich in organic compounds. These tholins are likely the result of solar radiation interacting with frozen methane, ethane, and other ices. This composition points to similarities with Kuiper Belt objects, though Sedna's origin and migration remain a mystery. Theories about Sedna's unusual orbit range from gravitational interactions with a passing star to the influence of an as-yet undiscovered 9th planet. Sedna's orbit may also provide clues about the formation of the Oort cloud, a distant shell of icy bodies that surrounds the solar system and serves as a reservoir for comets. Although no missions are currently planned to explore Sedna, its study through telescopes continues to provide valuable insights. As one of the most distant known objects, Sedna represents the solar system's boundary and raises intriguing questions about the forces that shaped its formation billions of years ago. Quaoar, the forgotten jewel of the Kuiper Belt. Quaoar, a lesser-known dwarf planet, quietly orbits within the Kuiper Belt, adding to the complexity and diversity of this icy region. Discovered in 2002, Quaoar was named after a Native American creation deity, reflecting its status as a harbinger of new knowledge about the outer solar system. With a diameter of about 1,100 kilometers, Quaoar is smaller than Pluto, but still one of the largest objects in the Kuiper Belt. Its surface is thought to be a mix of water ice and other frozen compounds, suggesting that it may have had a more geologically active past. Observations of its surface have also detected methane, ethane, and possibly ammonia, pointing to a chemically diverse environment. Quaoar's discovery challenged traditional assumptions about the size and composition of Kuiper Belt objects. Its relatively large size and spherical shape highlighted the potential for even more massive objects in this distant region, sparking a renewed interest in exploring the Kuiper Belt's hidden treasures. One of the most exciting findings about Quaoar is the detection of Waywatt, its tiny moon. This discovery has allowed scientists to study the system's dynamics, providing clues about Quaoar's mass and density. The presence of Waywatt also suggests that collisions and interactions in the Kuiper Belt may have played a significant role in shaping these distant worlds. Although Quaoar remains underexplored, its significance cannot be overstated. It represents a bridge between the well-studied worlds like Pluto and the smaller, more enigmatic objects that populate the Kuiper Belt. As technology advances, Quaoar will undoubtedly remain an essential target for understanding the formation and evolution of the outer solar system. The search for Planet 9 and its dwarf planet clues. The quest for Planet 9, a hypothetical massive world beyond Neptune, has reignited interest in the outer solar system. Dwarf planets like Sedna, Eris, and others may hold critical clues to the existence of this elusive giant, as their orbits hint at the gravitational influence of an unseen force. The theory of Planet 9 arose from observing the unusual orbits of several distant objects, including dwarf planets. These orbits cluster in a way that suggests the presence of a massive, unseen body exerting gravitational pull. If Planet 9 exists, it could be 10 times the mass of Earth and orbit the Sun at a distance of hundreds of astronomical units. The study of dwarf planets is central to this search. Their unique orbits act as breadcrumbs, leading scientists toward the regions where Planet 9 might reside. By tracking these objects with powerful telescopes, astronomers can piece together a map of the gravitational landscape beyond Neptune. While the search for Planet 9 is ongoing, its potential discovery would reshape our understanding of the solar system's architecture. It would also provide context for how dwarf planets form and interact with larger celestial bodies. Dwarf planets could reveal how gravity sculpts the solar system's outer reaches and affects the distribution of smaller objects. Whether or not Planet 9 is ever found, the search highlights the importance of studying dwarf planets. These distant worlds are not only fascinating in their own right, but also serve as critical tools for uncovering the hidden secrets of our solar system. The dwarf planets of our solar system showcase the incredible diversity and complexity of celestial bodies beyond the 8 major planets. From Pluto's icy plains to Haumea's rapid rotation, these worlds invite us to explore and learn more about the cosmos. If you enjoyed this deep dive, be sure to like, share, and subscribe to InnoVision Tech. Don't forget to hit the bell icon for updates on our latest content. Until next time, keep reaching for the stars with us. What if we told you that everything you see, touch, and experience began with a single, unimaginable explosion of energy and matter? The Big Bang Theory isn't just a theory. It's the story of how our universe came to life. From a tiny, infinitely dense point to the vast cosmos we marvel at today. How did this incredible journey begin, and what clues reveal our cosmic origins? Join us as we explore the birth of the universe, the forces shaping it, and what lies ahead in its vast, mysterious future. The Big Bang, the beginning of everything. The universe as we know it started approximately 13.8 billion years ago with an event known as the Big Bang. Far from being an explosion in space, the Big Bang was an expansion of space itself from a singularity, an infinitely small, dense, and hot point. In that fraction of a second, the laws of physics as we understand them came into existence, creating the foundation for everything in the cosmos. Within the first second, the universe expanded rapidly, a phenomenon called cosmic inflation. During this time, temperatures reached unimaginable levels, allowing the formation of the fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces. These forces govern the behavior of all matter and energy, making them the building blocks of the universe's structure. As the universe cooled, the first particles began to form. Quarks and electrons emerged, eventually combining to create protons and neutrons. These in turn formed the nuclei of the first atoms. Light particles or photons were released, marking the beginning of the universe's transition from opaque to transparent, a moment captured in the cosmic microwave background radiation that scientists study today. The Big Bang Theory is supported by compelling evidence. The observed expansion of the universe, first noted by Edwin Hubble, aligns perfectly with the idea that space itself has been stretching since the Big Bang. The discovery of cosmic microwave background radiation, a faint glow left over from the event, provides a snapshot of the universe when it was just 380,000 years old, offering a direct look at its earliest moments. Understanding the Big Bang is not just about looking into the past. It's about understanding how everything we see, from galaxies to the atoms in our bodies, came into being. It is the ultimate story of creation, a narrative that continues to inspire humanity's quest for knowledge. Cosmic inflation, the rapid expansion. The concept of cosmic inflation is one of the most fascinating aspects of the Big Bang Theory. In less than a trillionth of a second, the universe expanded exponentially, growing from a size smaller than an atom to that of a grapefruit. This rapid expansion set the stage for the universe's large-scale structure and explains many of its current properties. During inflation, tiny quantum fluctuations in the fabric of space were stretched to cosmic proportions. These fluctuations became the seeds of galaxies, clusters, and voids that would form millions of years later. It's mind-blowing to think that the intricate structures of the universe originated from minuscule variations in energy. Inflation also accounts for the universe's uniformity. Despite its vastness, the universe appears remarkably consistent in all directions. This homogeneity would be impossible without inflation, as it ensured that all regions of the universe were once close enough to share energy and information. Another key prediction of inflation is the formation of the cosmic microwave background radiation. As the universe expanded and cooled, light particles were able to travel freely for the first time, creating a snapshot of the universe in its infancy. This relic radiation provides critical evidence supporting the theory of inflation, showing subtle variations that align with the expected quantum fluctuations. While the idea of inflation is widely accepted, questions remain. What caused inflation to start and stop? And what happened to the energy released during this process? These mysteries keep scientists pushing the boundaries of our understanding, seeking answers that could reshape our view of the cosmos. Formation of matter building the universe's foundations. In the seconds and minutes following the Big Bang, the universe was a seething soup of particles. Protons and neutrons formed from quarks, and as the universe cooled, these particles combined to create the first atomic nuclei in a process known as nucleosynthesis. This critical period laid the groundwork for the chemical elements that would later form stars, planets, and life. The most abundant elements created during this time were hydrogen and helium, along with trace amounts of lithium and beryllium. These light elements make up most of the universe's observable matter today. Heavier elements, such as carbon and oxygen, wouldn't appear until much later, forged in the cores of stars. The distribution of these elements is remarkably uniform, a testament to the Big Bang's influence. Scientists measure this distribution using spectroscopy, comparing observations to theoretical predictions. The match between observed and predicted abundances is one of the strongest pieces of evidence for the Big Bang theory. As the universe expanded further, gravity began to take hold. Tiny variations in the density of matter caused particles to clump together, forming the seeds of galaxies and clusters. These clumps grew larger over millions of years, eventually creating the cosmic web of structures we see today. The story of matter's formation is one of transformation, from a chaotic high-energy state to the intricate structures that define the universe. It's a reminder of how complexity arises from simplicity, a theme that resonates across science and nature. The cosmic microwave background, a glimpse into the past. The cosmic microwave background, or CMB, is often called the baby picture of the universe. Discovered in 1964 by Arno Penzias and Robert Wilson, the CMB is a faint glow of radiation that permeates the universe, providing a direct link to the Big Bang. This radiation was released approximately 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form. Before this time, the universe was an opaque plasma, where light could not travel freely. The formation of neutral atoms allowed light to escape, creating the CMB we observe today. The CMB is not uniform. It contains tiny temperature fluctuations that reflect differences in the density of matter in the early universe. These fluctuations are the fingerprints of the initial quantum variations that were stretched during inflation. By studying the CMB, scientists can reconstruct the universe's history and refine their models of cosmic evolution. Modern telescopes, such as the Planck satellite, have mapped the CMB in incredible detail, revealing a wealth of information about the universe's composition, age, and shape. The data confirms that ordinary matter, and dark energy make up the universe, with the latter driving its accelerated expansion. The study of the CMB is a prime example of how scientific discovery builds on itself. From an accidental finding to a cornerstone of cosmology, the CMB continues to deepen our understanding of the universe's origins and its future. The evolution of galaxies from chaos to cosmic cities. Galaxies, the cosmic cities of stars, emerged from the aftermath of the Big Bang. They began forming roughly 100 million years after the universe's birth, as gravity worked on tiny fluctuations in the density of matter. These small irregularities, visible in the cosmic microwave background, grew over time into dense regions that became the cradles of galaxy formation. Initially, these protogalaxies were turbulent and chaotic, composed of gas clouds and newly forming stars. Over billions of years, they evolved into the diverse structures we see today, from spiral galaxies like the Milky Way to massive elliptical galaxies and irregular systems. This evolution was shaped by processes such as star formation, supernova explosions, and interactions between galaxies, including mergers and collisions. Galactic collisions played a significant role in shaping the universe. When galaxies merged, their shapes were altered, their star formation rates increased, and central supermassive black holes grew. The Milky Way, for example, is the result of countless mergers over billions of years, and it continues to interact with its neighbors, including the Andromeda Galaxy, which it will collide with in about 4.5 billion years. The formation of galaxies was also influenced by dark matter, an invisible substance that makes up about 27% of the universe. Dark matter provided the gravitational scaffolding necessary for galaxies to form and hold together. Without it, the visible matter we observe in the form of stars and gas would have dispersed rather than coalesced into galaxies. Galaxies are not just collections of stars, they are laboratories where the universe's history and future unfold. By studying them, scientists uncover clues about the conditions that shaped the cosmos and gain insights into the forces that continue to influence its evolution. The role of dark matter, the invisible hand of the cosmos. Dark matter is one of the universe's most enigmatic components. Although it doesn't emit, absorb, or reflect light, its presence is felt through its gravitational influence. It acts as the invisible scaffolding that holds galaxies and galaxy clusters together, playing a crucial role in the large-scale structure of the universe. Evidence for dark matter first emerged in the 1930s when astronomer Fritz Zwicky observed that galaxies in the Coma cluster were moving too quickly to be held together by visible matter alone. Later studies, including those of spiral galaxies by Vera Rubin, confirmed that the outer stars and galaxies orbit at unexpectedly high speeds, suggesting the presence of unseen mass. Dark matter is thought to form massive halos around galaxies, providing the gravitational pull necessary to maintain their structure. Without it, galaxies would not have enough mass to prevent their stars from drifting apart. This unseen material also helped amplify the density fluctuations in the early universe, enabling the formation of galaxies and clusters. Although dark matter's nature remains unknown, scientists have proposed various candidates, including weakly interacting massive particles or WIMPs and axions. Experiments on Earth, such as those conducted in underground laboratories and particle accelerators, aim to detect these elusive particles, while observations of cosmic phenomena provide indirect evidence. Dark matter's influence extends beyond galaxies. It shapes the cosmic web, a vast network of filaments and voids that define the large-scale structure of the universe. Understanding dark matter is key to solving many of cosmology's greatest mysteries and unlocking the secrets of the universe's formation and evolution. The ultimate fate of the universe, a journey into the unknown. The universe's fate is a question as profound as its origins. While the Big Bang marked the beginning of time and space, the cosmos is far from static. It is expanding, a fact first discovered by Edwin Hubble. The nature of this expansion holds the key to the universe's ultimate destiny. For much of the 20th century, scientists debated whether the universe would expand forever, slow down, or reverse in a big crunch. However, in 1998, observations of distant supernovae revealed that the expansion of the universe is accelerating, driven by a mysterious force known as dark energy. Dark energy, which constitutes about 68% of the universe, is the dominant factor shaping its future. If dark energy remains constant, the universe will continue expanding indefinitely, leading to a scenario called the Big Freeze. In this future, galaxies will drift farther apart, stars will exhaust their fuel, and the cosmos will grow cold and dark as entropy increases. Alternatively, if dark energy intensifies over time, it could tear apart galaxies, stars, and even atoms in a dramatic end known as the Big Rip. Another possibility is the Big Bounce, in which the universe's expansion eventually halts and reverses, leading to a new Big Bang. This theory suggests a cyclical universe with endless cycles of creation and destruction. Although less widely accepted, it raises intriguing questions about the nature of time and the potential for new beginnings. The ultimate fate of the universe remains uncertain, but each theory offers a glimpse into the vast possibilities of cosmic evolution. As scientists refine their understanding of dark energy and other cosmic forces, we move closer to unraveling the final chapter of the universe's story. The universe as a cosmic laboratory, a quest for understanding. The universe is more than a collection of stars, galaxies, and cosmic phenomena. It is a vast laboratory where the laws of nature are constantly tested. Every corner of the cosmos offers clues about its origins, evolution, and the fundamental principles that govern reality. From the tiniest particles to the largest galaxy clusters, the universe operates on a set of rules that scientists strive to decode. The interplay of forces like gravity, electromagnetism, and nuclear interactions shapes everything from the structure of atoms to the motion of galaxies. Understanding these forces provides a deeper appreciation of the universe's complexity and beauty. Telescopes and observatories, such as the Hubble Space Telescope and the upcoming James Webb Space Telescope, have revolutionized our view of the cosmos. They allow us to peer into the universe's distant past, observing light that has traveled billions of years to reach us. These observations provide a timeline of cosmic evolution, from the birth of the first stars to the formation of galaxies and beyond. Advances in technology have also enabled scientists to simulate the universe's evolution on supercomputers, recreating conditions from the Big Bang to the present day. These simulations help researchers test theories, predict cosmic phenomena, and understand the universe's large-scale structure. The universe is a living story, with each discovery adding a new chapter. As we continue to explore, we not only uncover the secrets of the cosmos, but also deepen our connection to the vast, intricate tapestry of existence. The story of the universe is as infinite as the cosmos itself, filled with mysteries, wonders, and profound questions. From the Big Bang to the distant future, every discovery reminds us of the incredible journey we are part of. If you enjoyed this exploration, be sure to like, share, and subscribe to InnoVision Tech. Don't forget to hit the bell icon to stay updated with our latest videos. Until next time, keep reaching for the stars and discovering the endless wonders of the universe. Have you ever looked at images of Saturn and wondered about the magnificent rings surrounding this gas giant? How did they form? What mysteries do they